Welcome to the video lecture on the integral test and p-series. In this video lecture, we're going to learn a couple of tests to determine the convergence or divergence of an infinite series. Let's start by considering the improper integral results of these two improper integrals. The first one is the integral from 1 to infinity of 1 over x dx. So if we wanted to integrate that, what we would need to do is first realize that we have that infinite bound up there, so we want to swap it out. So I'm just going to call it n and take the limit as n goes to infinity and change this to the integral from 1 to n of 1 over x dx. So we're turning this into a finite integral that we can integrate and then take the limit of that. Now, what is the antiderivative of 1 over x? Well, that's just the ln of the absolute value of x, and now we can plug in our bounds. So if we plug in our upper bound, we're just going to get the ln of n, and we're assuming here that n is positive since we're going to positive infinity, so I can drop those absolute values. And when I plug in 1, the ln of 1 is just 0, so this would just subtract 0. So what happens to the ln of n as n gets really, really big? Well, the ln of something really large stays large. So this is infinite, which means that we would suspect that if we looked at not the integral of 1 over x, but the sum of 1 over x from 1 to infinity, we might suspect that because the integral diverges, so might the sum as well. Okay? So this integral itself diverges. Now let's look at the integral from 1 to infinity of 1 over x squared dx. So they're very, very similar problems. This one we just have that extra square in the denominator, and let's see if that makes a difference. So first thing we're going to do is swap out that infinity with an n. Change this to the integral from 1 to n of 1 over x squared dx, which I'm going to rewrite as x to the negative 2. So the antiderivative of x to the negative 2 becomes x to the negative 1 over negative 1, which is the same as negative 1 over x. And now if I plug in my bounds, for n, I'm going to just get negative 1 over n, minus, when I plug in 1, I'm going to get negative 1. So this minus minus becomes plus, and the limit as n gets really, really big of 1 over n, that's going to go to 0. So this is just 0 plus 1, or 1, which means that improper integral converges. So what we're going to see is that there's this relationship between an improper integral of a function from 1 to infinity and the infinite series that it's related to. So if we think about the infinite series 1 over n as n goes from 1 to infinity versus the infinite series from 1 to infinity of 1 over n squared, what do you think the integral results that we just found imply about these series? Well, our guess would probably be that this infinite series is going to diverge because the improper integral diverged, and then this one here is probably going to converge because its improper integral converged. So let's see what that's actually called. That's called the integral test. And it's a very powerful test, but you have to make some assumptions and you have to show that a couple of conditions are true first before you can apply the integral test. First of all, you have to assume that your function f is positive, so it has to be above the x-axis, it has to be continuous, and it must be decreasing for every x greater than or equal to 1. Where we're going to let our a sub n, that expression that we see inside of our summation symbol, that's going to be our function of n, our f of n. And we're assuming n here is our positive integers ranging from 1 to infinity. And so what this integral test says is if you've met these conditions, that you've got a positive, continuous, and decreasing function, then the infinite series of a sub n from 1 to infinity and the integral from 1 to infinity of f of x dx, they either both converge or they both diverge. So if you can compute the improper integral from 1 to infinity and show that that converges or diverges, then you're proving that for the summation as well. So let's prove this integral test. To start off with, what we're going to do is we're going to create some approximations to the area under this curve from 1 to infinity. So we're going to be starting at 1, and I'm going to chop this up into rectangles, our good old rectangle method. And for this first one, I'm going to create inscribed rectangles, which would be using the right endpoints, the ones that are lower. So it would look something like this. So the area under the curve using inscribed rectangles would be the first height of this rectangle, which is actually f of 2, times its width, which is just 1. So f of 2 times 1, plus the rectangle area for the second rectangle here would be its height, which is now f of 3, this height right here, times its width, which is also 1, plus the next rectangle would have a height of f of 4 times its width, which is 1, and so on. And if we write that in summation notation, that would just be the sum of f of I, as I varies from 2 up to, say, n, if we do n rectangles. Now let's contrast that with the area of the circumscribed rectangles. So again, I'm going to chop up my interval into rectangles of width 1, but this time to get my circumscribed rectangles, I'm going to use the left endpoint. So this would be up this high, then if I use the left endpoint here, I'm going to be up this high, and so forth. So this area would be the left endpoint f of 1 times the width 1, plus this height, which is f of 2, times the width 1, plus f of 3, times the width 1, and so on. And then this time I'm only going to go as far as the left endpoint, which would be the n minus 1, whereas over here I was using the right endpoint, which would be all the way to n. So using n rectangles for the inscribed rectangles using the right endpoints, I would go from 2 to n. For the circumscribed rectangles, I'd go from 1 to n minus 1. And written in summation notation, this would be just f of I, as I starts at 1 and goes to n minus 1. Now think about s sub n. This is called our nth partial sum. So the nth partial sum is the sum of the first n terms in your series. So that would be a sub 1, a sub 2, a sub 3, all the way up to a sub n. And we're just calling these a sub n's our f's. So that would be f of 1, f of 2, all the way up to f of n. So this represents the nth partial sum. Now how does that relate to these two expressions that I have right here? So what you'll notice is that what we've got over here on the left is almost that nth partial sum, because it's got f of 2, f of 3, f of 4, all the way to f of n, but what it's missing is just f of 1. So this inscribed area right here, using those inscribed rectangles, is exactly the same as our nth partial sum minus that very first term, f of 1. And this circumscribed area is the same as not s sub n, the nth partial sum, but it would be the same as the n minus 1 partial sum, the sum of the first n minus 1 terms. So this sum right here is the same as s sub n minus 1, and this sum right here is the same as s sub n minus that very first term, f of 1, that it's missing. Now the true area under this curve, which we know as the integral from 1 to n of f of x dx, that's the exact area. We know that that exact area must lie between these two, because this inscribed rectangle area approximation is obviously a little bit too small because all these rectangles lie below the curve, versus over here in the circumscribed rectangle case, all these rectangles lie above. So this is calculating more area than what we want. So the true area is somewhere in between. So what we can say is that this integral from 1 to n of f of x dx, it's got to be greater than or equal to this inscribed case, which is our s sub n minus our very first term, f of 1. And the true area has to be less than the circumscribed case, which was our s sub n minus 1. So we have this sort of bounding relationship between our exact area and the nth partial sum and the n minus 1th partial sum. So now let's do a little proof here. what we're going to assume first is that this integral from 1 to infinity converges. So suppose that it converges to, say, L. Okay, so let's assume that this integral from 1 to infinity of f of x dx converges to some limit L. Then what we can say is that this s sub n minus f of 1 must be less than or equal to that L. This true area from 1 to n is going to eventually converge to L in the limit. So what we're going to say from this, if we add that f of 1 over to the other side, is that this nth partial sum is this L plus f of 1, which is basically just saying that the nth partial sum is bounded. It's got to be smaller than some value right here, whatever this value is on the right-hand side. So what this statement right here tells me is that s sub n is bounded from above. We also know from the initial assumption up here that we're talking about a decreasing function, that this is also monotonically decreasing. And we had a theorem in the video lecture on sequences that said if you have a sequence that is bounded and monotonic, then it must converge. So this implies by that theorem that this converges. And if the nth partial sum sequence converges, then that means that our actual series converges as well. So if the s sub n's converge, that implies that our sum, our infinite series here, must converge as well. So what we've just proven is that if we know the integral converges, that proves that the infinite series converges as well. Now what we're going to show is what happens if the integral diverges. So let's assume that the integral diverges, so we know that this integral from 1 to infinity of f of x dx diverges and goes to infinity. Then what we can say, based on this relationship up here, this inequality up here, we know that this integral from 1 to n of f of x dx is less than or equal to s sub n minus 1. And if this is going to infinity in the limit, then that's showing that s sub n is going to infinity in the limit as well. So this shows that the limit as n goes to infinity of this integral going to infinity diverging implies that the limit as n goes to infinity of these n minus 1 partial sums must also go to infinity as well, because the n minus 1 partial sum is supposed to be greater than or equal to something that's infinite. And the only way you can be greater than or equal to something that's infinite is if you are infinite as well. So that's showing that this limit of the sequence of partial sums here is diverging because its limit does not exist. So that statement, this limit statement right here, says that the sequence of these nth partial sums must diverge because they're going to infinity, and that means that the sum must diverge as well. Remember, whatever the sequence of nth partial sums is doing, that's what the summation, the infinite series, is doing as well. So if the nth partial sums are converging, then the series converges. If the nth partial sums diverge, then the series diverges. Okay, so there's our proof. So we're going to be using this integral test to show that if we're trying to find an infinite series, then if we can show that the improper integral converges or diverges, then that implies that the series converges or diverges as well. So let's look at an example. If we look at the series from 1 to infinity of n e to the negative n. Now, before we jump into this integral test, let's recall one test that we already know called the nth term test for divergence. And what the nth term test for divergence says is that if you have an nth term, this ne to the negative n, then the limit of that as n goes to infinity, if that limit is not 0, then your series will diverge automatically. So that's always a good test to quickly look for and see if it satisfies, because if it fails to have a limit that's 0, then you can stop right away and be done, and you automatically know that this will diverge. So that's what I'm going to do over here. I am actually using x's instead of n's, but it's the same idea. We want to know if this function right in here is going to go to 0 in the limit. So if we look at this limit initially, this is going to be infinity for the x is going to infinity, and e to the negative infinity is going to 1 over e to the infinity, which is like 1 over something really, really big. So this is going to 0. And that's one of our indeterminate forms, so it's not obvious what this answer is going to be. So what we can do to manipulate it is we can move that e to the negative x down to the bottom, just flip it down, and now this is going to infinity in the top, and e to the infinity is infinity in the bottom. And now it satisfies that criterion for L'Hopital's rule. So if we apply L'Hopital's rule, the derivative of the top is 1, the derivative of the bottom stays e to the x, and that means the top is fixed at 1, but the bottom is still going to infinity, and 1 over infinity is 0. So this is our nth term test right here. Now what does it mean if your limit doesn't equal 0? That means this must diverge. What does it mean if your limit does equal to 0? That doesn't tell us anything, unfortunately. We can't make a conclusion that this series diverges or converges. So the fact that this equal to 0 is good, but it doesn't tell us our final answer about whether or not this converges or diverges. So we can't conclude convergence or divergence yet. So that's when you pull out a different test to try. So that's what we're going to do next. We're going to try that integral test that we just talked about. So before we can use the integral test appropriately, we need to create a function. I'm going to call it f of x, which is exactly this formula here, but using x's instead of n's. So that's our x e to the negative x. And this function must be positive, continuous, and decreasing. Now, notice here that we're just using n's from 1 to infinity, or in this case x's from 1 to infinity. So you're only using positive x's, and we know that e to the x and e to the negative x is a function which stays above the x-axis anyway. So this is definitely going to be positive. And we also know that x is continuous and e to the negative x is continuous, so the product must be continuous as well. So those two requirements are satisfied. The one that's not as obvious is that this is a decreasing function. So let's go ahead and use some calculus to show that it must be decreasing. And that's to look at the derivative and show that the derivative is negative. So I'm going to take the derivative using my product rule. So I'm going to do the first times the derivative of the second, which would be e to the negative x back again times negative 1, plus e to the negative x times the derivative of x, which would just be a 1. And now let's go ahead and factor out our e to the negative x, and that'll leave me with a negative x plus 1. And if you want, you could rewrite this. On top, I'm going to make it a 1 minus x, and on the bottom, I'm going to have an e to the x. Now what you want to notice is this going to be negative? We know the denominator is always positive because e to the x is always positive. So it's only a question of when this denominator is going to be less than 0, and 1 minus x is less than 0 when x is greater than 1. So that's definitely going to be the case here. We can exclude that very first term at 1, but from that point on, from 2 to infinity, this is definitely going to be a decreasing function. And we'll have a theorem about this in a little while, but basically you can disregard a finite number of terms at the beginning that may not satisfy your condition of being decreasing. As long as eventually it does turn into a decreasing function, you're okay. All right, so this is going to be decreasing for all x greater than 1. So we have a function that's positive, continuous, and decreasing, so we're allowed to use the integral test. So what the integral test says is that you can look at the improper integral from 1 to infinity of our function x e to the negative x dx and see what it does. If it converges, then the series converges. If it diverges, then the series diverges. Now, in order to integrate this, we need a little bit of integration by parts. So we're going to let u be x and dv be e to the negative x. That means du is dx, and v would be the integral of e to the negative x, which we can't do without an extra little negative 1 in there, because this is e to the stuff. We need our stuff prime. So if we put in a negative 1, we have to counterbalance by a negative, and we're just going to get e to the stuff back again. So the integral of e to the negative x is negative e to the negative x. So this becomes the limit as n goes to infinity from 1 to n of x e to the negative x dx, which becomes the limit as n goes to infinity of u times v. So that's going to be negative x e to the negative x minus v, which is going to turn this to a positive, the integral of v du. And let's go ahead and finish that last integral. Oops. We are going to use that same comment that I made a moment ago about this being e to the stuff. So you have to have a negative 1 in there for your stuff prime, so you have to counterbalance by a negative. So this integral will be minus from the counterbalancing e to the stuff back again. And now we're ready to plug in our bounds. So this is going to be the limit as n goes to infinity of negative n e to the negative n minus e to the negative n minus, plugging in 1 is going to give me negative 1 e to the negative 1 minus e to the negative 1. So these two combine into a negative 2 e to the negative 1, which becomes a minus minus, or a plus 2 over e, if you will. And these, I'm going to rewrite them slightly. I'm going to take those negative exponents and move them down. So this would become negative n over e to the n minus 1 over e to the n. Now as n goes to infinity, this is going to go to infinity down here, which means this part goes to 0. This one, not so obvious because you have infinity over infinity. So using L'Hopital's rule on that, the derivative of the top is a negative 1, the derivative of the bottom stays e to the n, and now this goes to infinity, so the fraction goes to 0. So both of these go to 0, which means we're just going to have that 2 over e left. Now what you're looking for is just a finite value here, something that's not infinity. So the fact that this was an actual value means that this converged. And by the integral test, if the improper integral converges, then that means the sum from 1 to infinity of that n e to the negative n must converge as well. Okay? All right, let's try this again on a new function. Now we have 1 over n, the ln of n, quantity cubed. So if you do a quick little check again for that nth term test, you want to just do a quick check to see, okay, what happens as x goes to infinity? We want to make sure that this goes to 0, because if it doesn't go to 0, then we're done. We know this will diverge right away. This one is obvious because in the bottom you've got this going to infinity and the ln of infinity is still infinity. So this is acting like 1 over something infinite, which is going to obviously go to 0. So that means we can't tell. It could converge, it could still diverge. We just don't know unless we try something else. So we pull out our integral test. Usually you're going to want to use the integral test whenever this nth term right here looks like something you could probably integrate. Okay, and this does. This looks like a good candidate for a u substitution. But before we do that, we need to define our function. So 1 over x ln of x quantity cubed. We want to make sure that it's positive, which it will be for x is bigger than 2, because ln of 1 is 0. Anything less than 1 ln is actually negative. But if we're starting our n at 2 here, ln of 2 and beyond is positive. So these two denominators will be positive. X is continuous, ln of x quantity cubed is continuous, 1 over that's going to be continuous. So now we just have this question of the decreasing. So this is going to be true for our x is greater than or equal to 2. Let's see about our derivative. Now, to do the derivative here, you can do this any number of ways. If you want, actually, let me back up here a second. Let's rewrite our function as x to the negative 1 and ln of x to the negative 3. I'm moving them both up to the top just so that for my personal preference would be to use the product rule here instead of maybe having to apply a quotient rule. So I'm going to use a product rule on this. So it's going to be the first function times the derivative of the second, and you need a chain rule there. So we bring down the negative 3, subtract 1 from the power, and multiply by the derivative of what's inside, which is a 1 over x, or an x to the negative 1, plus the second function times the derivative of the first. So I bring down the 1 and I subtract 1 from the power. Notice that x to the negative 1 and x to the negative 1 is an x to the negative 2. So both of these terms here and here share an x to the negative 2, which I'm going to pull out. They both have a negative, and they both have an ln of x, and you want to pull out the smaller of the two powers, which is the negative 4. So if I pull that out, this is gone, this is gone, this is gone, this is gone. All I have left is the 3. Over here, this is gone, but I have 1 left because ln of x to the negative 4 times an ln of x to the positive 1, when you add those powers, negative 4 plus 1 gets you back to negative 3. So rewriting this is going to be 3 plus ln of x on top. We'll have a negative x squared and ln of x to the 4th on the bottom. Now that denominator's always negative because x squared is positive and something to the 4th is positive, so this negative out front will remain. The top is always positive. Remember when we're using x is greater than or equal to 2. So that means this will be negative, and therefore the function is decreasing as long as we're looking at x is greater than or equal to 2, which we are. Okay, so we're ready to use our integral test. So the integral test says that we're going to look at the integral, and remember here our summation was starting at 2. So I want to go from 2 to infinity. So my integral is going to go from 2 to infinity of our function, which was 1 over x ln of x quantity cubed dx. So we're going to change this to a limit, change that upper bound to an n, and I'm going to recognize that the integral test is a good choice here because you only want to really use the integral test when what you have inside here looks like something that you can integrate. And this is ideal for a u substitution because if I let u be ln of x, then du is 1 over x dx, which is exactly what I have here and here. So this is going to turn into the integral of 1 over x dx becomes our du, and 1 over ln of x cubed becomes 1 over u cubed, or u to the negative 3. I'm going to leave off my bounds initially here because the 2 and the n are actually x bounds, not u bounds. So I'll convert back in terms of x and then I'll use the 2 and the n. But for now, let's just leave the bounds off. When I integrate u to the negative 3, I add 1 to the power, which makes it negative 2, and then I divide by the new power. So that means this is going to turn into negative 1 over 2u squared, and if I substitute back in terms of x, that u just changes back into an ln of x. So we're going to get negative 1 over 2 ln of x quantity squared, and now we're ready to use our bounds from 2 to n. So if we plug in our n, that upper bound, this becomes negative 1 over 2 ln of n quantity squared minus, if I plug in my 2, I'm going to get negative 1 over 2 ln of 2 squared. Minus minus becomes a plus. Now as n gets big, the ln of infinity stays big. So this is going to infinity, which means this fraction is going to 0. So what we end up with here is 1 over 2 ln of 2 quantity squared. Now that's some decimal. I don't know what the ln of 2 is off the top of my head, but this is just some decimal. And all we care about is the fact that it's some finite value. So this tells me that the improper integral converges. And by the integral test, that implies that the series from 2 to infinity of 1 over n ln of n quantity cubed converges as well. Alright, if we look at the next example here, we want the sum from 1 to infinity of the ln of n. So if you jump right into the integral test here, you would probably let your function f of x be ln of x, and for x from 1 to infinity, for x is greater than or equal to 1, ln of 1 is positive and it is continuous. And that's true as long as we're greater than or equal to 1. So then if we try to show that this is decreasing, we would look at the derivative, and the ln of x is going to have a derivative of 1 over x. Now remember, we're looking at x's greater than or equal to 1, which are positive x's. So if we're plugging in a positive x here, then this is going to be greater than or equal to 0. And in fact, it's just going to be greater than 0, because that numerator is never going to equal 0. And that's not what we want. That is actually showing that our function f is an increasing function, not decreasing. So the fact that this is increasing and not decreasing means we can't use the integral test. You have to have these three conditions being met: positive, continuous, and decreasing. So if any one of those fails, then you can't apply the integral test. So the other only option that we have here is to maybe check for that nth term test. So if we take a look at the limit of this nth term as n is going to infinity, or the limit of ln of x as x is going to infinity, what is that doing? Well, the ln of infinity is infinity, and this is not 0, which is what you need to have for it to possibly converge, or it could still diverge even if it is 0. But the fact that it's not 0 automatically means that this series from 1 to infinity of ln of n must diverge by the nth term test. So don't overlook that test, because it's a really quick, easy way to find out if something diverges or not. Now if we look at this one here, and we apply that nth term test on it right away, then we would look at the limit as x goes to infinity of ln of x over x. Now initially, this is going to infinity on top and infinity on the bottom. So if we apply L'Hopital's rule, the derivative of ln of x is 1 over x, the derivative of x is 1. So this is acting like the limit as x goes to infinity of just a 1 over x, and that does go to 0. So that means we can't conclude convergence or divergence based on this nth term test. So we have to try a different test. So let's try the integral test, because to me this looks like something that I could integrate. Now before I use the integral test, let's define our function. So ln of x over x. If x is greater than or equal to 1, then ln is going to be positive and x will be positive. So this is a positive function, and ln and x are both continuous. And this is going to be true for x greater than or equal to 1. Now let's see if it decreases. So let's go ahead and just use our quotient rule here. So I'm going to do low d high, so the bottom times the derivative of the top, minus the top times the derivative of the bottom over the bottom squared. x times 1 over x just becomes 1. So this is 1 minus ln of x over x squared. Now that denominator is always positive because of the square. So what about 1 minus ln of x? Well, 1 minus ln of x is going to be less than 0 when ln of x is greater than 1. And you can actually solve this by undoing the ln using a base of e. This is base e right here. So if I take e and raise it to the first power, then that means this numerator will be less than 0 as long as x is greater than or equal to greater than e, which is about 2.7. So this derivative will be less than 0 for x is greater than or equal to 3, the next biggest integer. So this is what I was mentioning earlier about it's okay if the first couple of terms here do not satisfy your condition of being decreasing, as long as eventually you can find an end where it continues to be decreasing from that point on, then you're okay. You can disregard those first few finite terms, and as long as eventually it does become decreasing afterwards. So this is decreasing as long as our x is greater than or equal to 3. So now if we go ahead and look at the integral, this will become the integral from 1 to infinity of the ln of x over x dx, which is going to be the limit as n goes to infinity from 1 to n of ln of x over x dx. And using a u substitution here, the u will be ln of x, the du will be 1 over x dx, which is what I have right here. So this just becomes the limit as n goes to infinity of u for the ln of x, and then the dx over x becomes du. And that is just u squared over 2. Turning it back in terms of x, make sure you use your x's here before you use your bounds. So this becomes the ln of x squared over 2. And now if we plug in our bounds, this is going to be the limit as n goes to infinity of the ln of n squared over 2 minus, when I plug in 1, the ln of 1 is 0. 0 squared over 2 will stay 0. As n goes to infinity, the ln of infinity stays infinite. So this is infinity, which means this whole thing goes to infinity, which means this diverges. So by the integral test, this series ln of n over n, as n goes from 1 to infinity, must diverge as well. It will do the same thing that the integral does. So here's that theorem that I was mentioning. For any positive k, the series from 1 to infinity of a sub n, which would be a1 plus a2 plus a3 and so on, and the series of a sub n starting at k and going to infinity, so that would just be a sub k plus a sub k plus 1 and so on, either both converge or both diverge. So what that means is that the first k terms will not affect the convergence or divergence of an infinite series. So if those first few finite terms, those first k terms, do not decrease, for example, that's okay, as long as you can find a k where eventually it will decrease from that point on, then you can base your conclusion on convergence or divergence on those k terms starting from that kth term on. Okay, so it's okay if the first finite terms, k finite terms, do not satisfy your conditions, as long as the rest of them do. Now the next thing we're going to look at is another test that we can use called a p-series. And this is a theorem on the convergence and divergence of a p-series. Now a p-series is anything of the form 1 over n to the p, or 1 over x to the p. So this would be 1 over 1 to the p plus 1 over 2 to the p plus 1 over 3 to the p and so forth. This is called a p-series, and it converges if your power p is greater than 1, and it will diverge if your power p is less than or equal to 1. So here's the proof. Since f of x equals to 1 over x to the p is a continuous, positive, and decreasing function, it's decreasing because the derivative of 1 over x to the p, when you use the power rule, gives you negative p over x to the p minus 1. Our x's are positive, so this denominator will be positive, but the numerator is obviously negative. So this will definitely be decreasing for p greater than or equal to 1. So since we're continuous, positive, and decreasing, we can use the integral test. So if we look at the integral from 1 to infinity of 1 over x to the p dx, this is actually something that we have proven in a previous video lecture. If we look at that improper integral, we've proven already that it will only converge if p is greater than 1, and it diverges if p is less than or equal to 1. And so if this improper integral converges, then the series will converge. So that's only going to happen if your p is greater than 1. This improper integral will diverge if your p is less than or equal to 1, so will the series. Now notice that the series 1 over n to the 1, where your p is 1, that's just the sum of 1 over n. This is called the harmonic series. It's a very famous series, so it has its own special name. So this is the p series when p is 1, and it's called the harmonic series. And we've actually proven already in the past that it does diverge, but we're going to see another proof of that in a little while. Now note, this is important, that even though we know whether or not a p-series converges or diverges, we know that if it does converge, we don't know what it necessarily converges to. Okay, so even though we might know that it converges, we don't know what it converges to. We don't know what the actual sum is. The only ones that we know how to find the actual sum of are ones where we know the formula for the nth partial sum, and if we take the limit of the nth partial sum, that will be what the infinite sum is. Or the other case is if we know that we have a geometric series that converges because your r is less than 1, then what you know is that the sum of an infinite series is a over 1 minus r. Those are the only two types of infinite series where we can actually compute the sum. So let's apply our p-series formula here, or theorem, to these series. And these should be really quick and easy to do, because these are just 1 over n raised to a power. So this is your p. P is that power. And what we said is that as long as that p is greater than 1, it will converge. If it's less than or equal to 1, like this one is, then the series will automatically diverge. So if we look at this p is 4/3. 4/3 is greater than 1, so that means this will automatically converge because of our p series. This power p is pi, and pi is 3.14, so that's bigger than 1, so that means this series is going to converge as well. And when you're explaining this, you can just say that it converges because it's a p series with p bigger than 1. How about number 8 here? Does this look like a p-series? No, because it's not 1 over n raised to a power. It's actually a constant raised to a power. This is actually a geometric series. We talked about these in a previous video lecture. This is your r. And what we said in our previous lecture is that your r needs to be a fraction. It can be a positive or a negative fraction less than 1. And this is obviously greater than 1, and a geometric series where your r is bigger than 1 will automatically diverge. It's only going to converge if it's a fraction that's less than 1 in absolute value. How about this series here, 1 over n squared minus 1 over n cubed? Well, what we'll see here is that we don't necessarily know or can rewrite this initially as a p-series, a single p-series, but you can break it up or think of it as two separate p-series. We know that this one right here is a p-series where your p is 2, which is greater than 1, so this particular series must converge. And this one over here is also a p-series with your p equal to 3, which is greater than 1, so it must converge as well. So if you have two sequences which you know converge, then the difference of the two must converge as well. So you can think of this, if you want, as these two individual series being subtracted from each other. And since each one converges, the entire difference of the two must converge as well. Now, on this next page, we're going to talk about an alternate proof of the divergence of the harmonic series. Remember, the harmonic series is that series of just the nth term being 1 over n. So this is the series that's 1 plus a half plus a third plus a fourth plus a fifth plus a sixth, and so on. Now you can compute some of those partial sums. So the first partial sum would just be 1. The second partial sum would be 1 plus a half, which is 1.5. The third partial sum would be 1 plus a half plus a third, which is 1.83, and then so on. S4 is 2.08. The 100th partial sum is 5.19, all the way up to the 248,642th partial sum is about 13.0067. So you can see that these nth partial sums, they're slowly getting bigger and bigger, and we can go out quite far and still only be at 13. So we're going to show that this actually does diverge, and we're going to do it in kind of a clever way. So here's my harmonic series. I've got 32 terms written out here so far, and I'm going to continue this to infinity, but I'm grouping them in a certain way. What you want to notice is that in this first grouping right here in the parentheses, 1/3 we know is a fraction that is bigger than 1/4, correct? So that means this sum of just these two terms would be greater than 1/4 plus 1/4. These two match, and this one is bigger than this one. So this sum in parentheses is going to be bigger than a fourth plus a fourth, which we know adds to a half. So this stuff in parentheses must be bigger than a half. If we look at these next four terms, we know that all three of these fractions here, here, and here, they are all bigger than 1/8 because their denominators are smaller. So this would be bigger than 1/8 plus 1/8 plus 1/8 plus 1/8, which is 4/8, which is a half. So these four terms add to something that's bigger than a half as well. If we go to the next group of terms, each one of these is going to be bigger than a 16th. A 16th plus a 16th plus a 16th, and so on, all the way up to that 1/16. And there's 8 of those. 8/16 is a half. Similarly here, all of these fractions leading up to that 32 are going to be bigger than 1/32. And there's 16 of those between 17 and 32. So 16/32 is a half. So I'm grouping these in a special way to show that in those parentheses, each of those sums can be sort of approximated by this 1/2, and the true sum is going to be bigger than it. So what we're going to see here is that the fourth partial sum, which would be the first term 1 plus the second term, which is a half, plus the third term plus the fourth term, this, since these two are greater than a half, then this sum is going to be 1 from this one, a half from this half, plus I'm going to approximate these two by a half as well. So the true fourth partial sum is actually going to be greater than 2. The eighth partial sum, which we know is 1 plus a half plus a third plus a fourth plus a fifth plus a sixth plus a seventh plus an eighth, if I group these, then this sum, this true sum here, is going to be larger than 1 plus a half plus these two I know are greater than a half, so this side is greater than a half, and these four are greater than a half as well. So that's going to be 1 plus 1 plus a half, which is 2.5. So the 8th partial sum is larger than 2.5. If I go to the 16th partial sum, then that's going to be this one here, this 1/2 here, these two which are greater than 1/2, these 4 here which are greater than 1/2, and these 8 here which are greater than 1/2, and that gets me all the way to the 16th term. And if you add all that up, that's 1 plus 1 plus 1, so that's 3. If we go all the way to the 32nd, the 32nd is this 1 plus this 1/2 plus these 2 which make 1/2, these 4 which make 1/2, these 8 which make 1/2, and these 16 which make 1/2. I'm not saying that's what the actual sum is. I'm saying that the true sum is going to be larger than that, right? So this is 1 plus 1 plus 1, that's 3.5. Now look at the pattern here. 4 is 2 squared, so I used 2 1/2. 8 is 2 cubed, and I used 3 1/2. 16 is 2 to the 4th, and I used 4 1/2. 32 is 2 to the 5th, and I used 5 1/2. So if we come up with a formula here, the 2 to the kth partial sum will be this 1 plus k 1/2. So we're basically coming up with a formula here. So for example, the 2 to the 12th partial sum would be 1 plus 12 1/2, which is 6 plus 1 or 7. And the 2 to the 18th partial sum would be 1 plus 18 1/2, which is 1 plus 9 or 10. So what we can show here is that for any n greater than 0, what we want to know is when is this 1 plus k to the 1/2 going to be bigger than n. So our nth partial sum, or let me rewrite this as s to the 2k, which we're going to call our little n here, that is equal to our formula 1 plus k 1/2, and we want to know when is that nth partial sum going to be larger than this random number I pick. Suppose I want to find out when is this sum going to be bigger than 1,000. Well, I set my formula greater than n, and if we solve this for n, solve this for k, let's see what we get. We're going to get 1/2 k greater than n minus 1, and if I go ahead and I multiply both sides by 2, that means I can always pick my k to be 2n minus 2, and that will give me my sum always greater than n. So if we pick k equal to 2 to the n minus 2, then the 2 to the 2n minus 2 partial sum must be larger than n, which means you can pick this n to be anything you want, as large as you want. So that means I can make this nth partial sum get as large as I want. And if I can make it get as big as I want, I can make it get infinite. And that means these nth partial sums diverge, which means the series diverges. Okay, so what we're showing here is that it's possible to pick any n as big as you want, and that will correspond to some power k here, so that the s to the 2k partial sum will be bigger than that really large number that you pick. And if you pick your n to continually be bigger and bigger and bigger, eventually you can get it to be infinite, and that's going to show that those nth partial sums are getting infinite as well. And if your nth partial sums are infinite, then that means that they diverge, so your series diverges as well. So if we have to figure out how many terms of the harmonic series are needed to obtain a sum greater than 20, that means we're trying to figure out when is our nth partial sum going to be bigger than 20. Well, the nth partial sum formula that we had, that we just derived, was 1 plus k 1/2. So let's figure out what our k would need to be to make this nth partial sum be larger than 20. So if I solve this, I'm going to get 1/2 k is greater than 19, and if I multiply by 2, I'm going to get 38. Now remember, this nth partial sum is actually 2 to the k. And so in this example, our k is 38. So this would be 2 to the 38th. So the 2 to the 38th partial sum is going to be larger than 20. And 2 to the 38th, just so you know, is 2.7 times 10 to the 11th. So that's 2 and then 7 followed by 10 zeros. So if I go out super far in my sequence, eventually adding up all of these terms, I'm going to get a sum that's bigger than 20. So I have to go out really far, but eventually that sum will be larger than 20. That's what we're showing. So I would have to add 1 plus a half plus a third plus a fourth plus a fifth all the way to 1 over 270,000, etc. And that sum is going to be bigger than 20. So how many terms does it take for the sum to be greater than 100? So what would my k need to be so that my nth partial sum is bigger than 100? Well, my formula for my nth partial sums are 1 plus a half times k. Whoops, this is supposed to be a 1 here. So if I subtract 1, I'm going to get 99. If I multiply by 2, that's going to be 198. So I need to pick the partial sum that's 2 to the 198th, and that will give me a sum that's bigger than 100. And 2 to the 198th is 4.017 times 10 to the 59. So I would need to go out that many terms in my harmonic series. So 1 plus a half plus a third plus a fourth all the way out to 1 over this number. Add up all those fractions and it'll add up to something greater than 100. How many terms would it take to get a sum greater than 1660? So I want my nth partial sum to be bigger than 1660. So that means I need to take 1 plus 1/2 k and force it to be bigger than 1660. So I get 1/2 k greater than 1659, and when I multiply by 2, that's 3,318. So I would need 2 to the 3,318th, and that nth partial sum will be greater than 1660. What this is showing me is that this series, 1 over n, from 1 to infinity, is a very slow growing sum that diverges. I can pick any number here on this right hand side that you want. You could pick 1,000,000, a gazillion, whatever number you want that's really large, and there's going to be a k that will eventually get you to an nth partial sum that's bigger than that. So that's why this is diverging, because you can pick this number over here to be as large as you want, and your nth partial sum will be bigger than that. So it's not converging because it's getting bigger and bigger. It's just doing it really slowly because I have to go so far out in order to get my sum to be this big. Here are some miscellaneous results, or theorems if you will. If you know that you have a sum a sub n and a sum b sub n that are both convergent, then the sum of the two converges, and a constant times a convergent sum will also converge. And we discussed this, or we did this already with that p-series example of 1 over n squared minus 1 over n cubed. If you have a divergent series, multiplying it by a constant will keep it divergent. If you have a convergent series a sub n and a divergent series b sub n, then the sum of a sub n plus b sub n will be divergent. So if either one of these diverges, then the whole thing diverges. And if you have a sub n and b sub n both being divergent, then no conclusion can be drawn regarding the sum. So for example, if I want the sum of 1 over n, which we know diverges because it's a p-series, it's that harmonic series, plus the sum of 1 over 2 to the n, which we know diverges because it's just the constant 1/2 times the divergent harmonic series. What would the sum of these two be if I added 1 over n to 1 over 2n? Well, if you get a common denominator, this is going to be 2 plus 1, or 3/2 times 1 over n. And that diverges because that's a constant 3/2 times the harmonic series, which diverges. Now what if we look at 1 over n plus negative 1 over n? Well, 1 over n diverges because it's the harmonic series, and negative 1 over n diverges because it's just a negative times a divergent series. But what happens when I add these two together? Well, 1 over n plus a negative 1 over n is just 0. And the sum of 0 is just 0, which does converge. So if both of them diverge, then you can't conclude whether it's going to diverge or converge. You have to be a little bit more creative. If only one of them diverges and the other converges, then it will diverge. And that's what this statement or theorem up here was saying. If you know one of them converges but the other doesn't, then it will diverge. But if both diverge, you don't have enough information to tell. Now, although the integral test can be used to determine whether or not an infinite series converges or diverges, it does not indicate what a convergent series converges to, so that it doesn't tell us what that sum actually is. So what we're going to do now is we're going to investigate a method in which we can find an approximation to the sum of a convergent infinite series if the series satisfies the hypotheses of the integral test. What we're going to do is we're going to define the remainder of a series by this r sub n, and it's represented by the sum of all the terms of the whole sum minus the first n terms of the sum, which is going to be that s sub n. So the remainder is the full sum minus the first n terms. So if you think about a positive, continuous, decreasing function, you have to have those three conditions so that you have some kind of graph like this. Then your nth partial sum would be a sub 1 plus a sub 2 plus a sub 3 all the way up to a sub n. The full sum s would be a sub 1 plus a sub 2 plus a sub 3 all the way up to the infinite number of terms. So the remainder, what we're defining this remainder to be, is I'm taking away these first n terms, and that's this s sub n up here, and the remainder is going to be what's left. So that's going to be my r sub n. So r sub n is the full sum minus the first n terms. So it's just the sum of the nth plus 1 term on. And what we know is that this remainder has to be less than or equal to the true area from n to infinity of f of x dx. Because if you think about your nth rectangle over here, say that this is n, n plus 1, n plus 2, and so on, then the remainder is just your inscribed area from here and so forth. And that area, using those rectangles at a height of n plus 1, a height of n plus 2, with a width of 1, those inscribed rectangles have an area that is less than or equal to the true area from n all the way to infinity. Okay? So how do we use this? Well, what we can do is we can approximate the sum of a series, and this series that we're going to look at is 1 over n to the 5th, so that's a p series. Therefore, we know it converges because our p is 5, and that's bigger than 1. So let's approximate this convergent series sum using the first 4 terms. So that's what I have right here. When n is 1, we get 1. When n is 2, we get 1 over 2 to the 5th. When n is 3, we get 1 over 3 to the 5th. And when n is 4, we get 1 over 4 to the 5th. And that as a decimal is about 1.0363 and so forth. So that's our approximation for the true sum of the series. Now, by doing that approximation, how much error have we maintained? How much error have we incurred because we're stopping after that fourth term? So we want to estimate the maximum error approximation. And that's going to be this remainder that we're talking about. So if we're using the first four terms, then the remainder based on those four terms, according to this statement that we have right here, the remainder will be less than or equal to the integral from n up to infinity. So the remainder of the first four terms has to be less than or equal to the integral from 4 to infinity of our function 1 over x to the fifth dx, which is a positive, continuous, and it's a decreasing function. You can just look at the graph of it to see that it decreases. It's going to look just like our graph that we had earlier. So if we have this integral, let's see if we can evaluate it. I'm going to change that infinity symbol to a b and make this the limit as b goes to infinity of the integral from 4 to b of x to the negative 5 dx. To integrate x to the negative 5, we add 1 to the power, which makes it a negative 4 over the new power, negative 4. And now we're ready to plug in some bounds. Now I'm actually going to flip this around a little bit first. This is the same as negative 1 over 4x to the fourth. So if I plug in b, this becomes negative 1 over 4b to the fourth minus negative 1 over 4 times 4 to the fourth. Now as b goes to infinity, this goes to infinity, so the whole fraction goes to 0. So this will be 0, and minus minus becomes plus, and 4 times 4 to the fourth is 4 to the fifth. And 4 to the fifth is approximately 0.00099765. So what we've just shown is that this remainder, r sub 4, is less than or equal to the value of this improper integral, which we just found out was 1 over 4 to the fifth, or 0.0009765. So what this means is by using these first four terms and approximating the actual sum by this number, we're off at most by this amount of error. So the true sum is this plus or minus this value right here. Okay, so this is called your remainder. All right, let's try one more example like that. Determine the number of terms to include in the sum in order to find the sum of 1 over n to the 3/2 from 1 to infinity, so that the truncation error, or the remainder, is less than or equal to 0.001. So first of all, this series right here converges because it's a p series where our p is equal to 3/2, which is bigger than 1. So that means this is definitely going to converge to some value. We just don't know what that value is. We don't know what the sum of this actually is. So we're going to figure out how accurate we can get to the true value of the sum as long as we're within an error of 0.001. So what our integral test tells us is that this remainder, r sub n, has to be less than or equal to the integral from n to infinity of our function, which I'm going to use x's here, but this would be 1 over x to the 3/2 dx. And that means if I convert this to our limit notation, the limit as, I got to use a different letter than n, let's use that b, so the limit as b goes to infinity from n to b, I'm going to rewrite this 1 over x to the 3/2 as x to the negative 3/2 dx. If we can find a value for this improper integral, that will give me a bound on my remainder. So what is this integral going to be? The power rule, when I add 1 to the power, this is going to become x to the negative 1/2 with the reciprocal out front. Let me go ahead and rewrite that as negative 2 over the square root of x. So when I plug in my bounds, this will be negative 2 over the square root of b minus negative 2 over the square root of n. Now as b goes to infinity here, the fraction is going to go to 0. And a minus minus right here becomes plus. So this is 2 over the square root of n. So what we're saying is that our remainder, r sub n, is less than or equal to that value. And we want that value to be less than or equal to that truncation error of 0.001. So this gives us an inequality which we can solve. So what I'm going to do is I'm going to multiply the square root of n over to the right side. Then I'm going to divide everything by 0.001. 2 divided by 0.001 is now my left side. And if I square both sides, then that's going to give me n. And when you take 2 over 0.001 and square that, you're going to get 4 million. Because 2 divided by 0.001 is 2,000. And when I square that, I'm going to get 4 million. So this means that I need to go out as far as the 4 millionth term. I need my n to be all the way to 4 million in order for the true sum to be accurate within 0.001. Okay, so if I go out to the 4 millionth term up here, if I go all the way to 4 million up here, and add up those first 4 million terms, that sum is true or accurate to the true sum within 0.001. That's how much accuracy I have. All right? So you can use this remainder sort of theorem, if you will, to tell you how far out you need to go to get within the accuracy level that you're looking for the true value of the sum. Alright, that concludes our video lecture on the integral test and p-series. Good luck!